Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into a question that sounds simple at first, yet becomes stranger the longer you think about it. Why does time stop for light? Light leaves distant stars and crosses the universe to reach us. Some of the light entering your eyes tonight began its journey before human civilization existed. It travelled across vast darkness, passing silent galaxies and drifting through empty cosmic voids. By our clocks here on Earth, that journey might have taken thousands, millions, or even billions of years. And yet, according to the physics discovered by Albert Einstein, something remarkable is true. For the light itself, no time passed at all, not 1 second, not even the smallest fraction of a second. A journey that takes billions of years for us takes zero time for light. At first, this sounds impossible. How can something travel for ages and yet experience no duration at all? But this idea is not poetic speculation or science fiction. It falls directly out of the structure of space and time themselves. Tonight, we will explore this strange truth slowly and gently. Along the way, we will discover why clocks slow down when they move fast, why the speed of light has a special place in the universe, and how motion through space is quietly connected to motion through time. We will see how physicists think about something called spacetime, where distance and duration are woven together into a single fabric, and we will follow the path of a tiny particle of light, a photon, as it travels across unimaginable cosmic distances while its own clock remains completely still. But before you settle in too deeply, I'd love if you could take a moment to like this video and subscribe, only if you truly enjoy these quiet explorations of science and the universe. And when you're ready, leave a comment telling me where in the world you're listening from and what time it is for you right now. It's always wonderful to see all the different places we gather from, each in our own little corner of time. Now feel free to dim the lights, maybe turn on a fan for a soft background hum, and let your mind drift gently with the story. And if your thoughts wander, that's perfectly fine. We will still be here, quietly exploring the strange relationship between light and time, and it begins with a journey so long that it reshapes our understanding of the universe itself. Tonight, let us begin with a quiet thought experiment. Imagine a distant star, so far away that its light takes 1 billion years to reach Earth. 1 billion years is almost too large for the mind to comfortably hold. During that time, continents drift across oceans, entire species appear and vanish, mountains rise, erode and fade into valleys of dust. While that light is travelling, life on Earth might change completely. Civilizations might rise, flourish and disappear again, and yet something very strange is hidden inside that enormous journey. According to modern physics, the light itself does not experience those billions of years at all. From the light's own perspective, if we can cautiously use that phrase, the departure from the distant star and the arrival at your eye happen at the same instant. The entire journey takes no time. It is as though the photon leaves the star and arrives here immediately, even though our clocks say that billions of years have passed. At first glance, this seems impossible. Our everyday intuition tells us that travel always requires time. If you walk across a room, a few seconds pass. If you drive across a city, perhaps an hour passes. If a spacecraft crosses the solar system, it may take months or years. Distance and time appear inseparable. But the universe, as it turns out, is not quite as simple as our everyday experience suggests. The key to understanding this mystery lies in the strange relationship between motion and time. To see why, imagine something very familiar: a clock. When you glance at a clock on your wall, it seems like a simple device marking the passage of time. But if we look a little closer, every clock is really just a repeating physical process. A pendulum swings back and forth, a quartz crystal vibrates steadily. Inside an atomic clock, atoms oscillate between energy states with extraordinary precision. Each repetition becomes a tick. Each tick becomes a measure of time. In this sense, time is not something separate from the physical world. It is simply the counting of processes that repeat again and again. If those processes slow down, then time, at least for that system, slows down as well. And here is where the story becomes interesting. Imagine two identical clocks sitting side by side on a table. Their ticking is perfectly synchronized. 1 second passes for one clock and 1 second passes for the other. They agree completely. Now imagine taking one of those clocks and placing it on a spaceship that begins to travel very fast through space. From the point of view of the traveller, nothing unusual happens. The clock ticks normally. Seconds pass just as they always have. Life on the spaceship feels perfectly ordinary. But from the perspective of someone watching from Earth, something surprising occurs. The moving clock ticks more slowly. Not because it is damaged, not because it is malfunctioning. It simply runs at a different rate because it is moving. This phenomenon is called time dilation, and it has been confirmed again and again by careful experiments. Atomic clocks flown aboard airplanes return showing slightly less elapsed time than identical clocks that remained on the ground. Satellites orbiting Earth experience small differences in time compared with clocks on the planet's surface. Even tiny particles created high in Earth's atmosphere survive longer when they move at extremely high speeds. Time itself changes depending on motion. At everyday speeds, walking, driving, flying, this effect is far too small for us to notice. But as an object moves faster and faster, the difference grows larger. At speeds approaching the speed of light, time slows dramatically. A clock travelling near that speed might tick only once, while a clock on Earth ticks many times. Push this idea all the way to its limit, and the result becomes astonishing. If something could move exactly at the speed of light, its clock would stop completely. No ticks, no seconds, no passage of time. Light itself travels at this extraordinary speed, roughly 300,000 kilometers every second. It crosses the distance between Earth and the Moon in little more than a second. It travels from the Sun to Earth in about 8 minutes. Yet because it moves at the cosmic speed limit of the universe, its own measure of time does not advance at all. This is why physicists sometimes say that light exists outside the normal flow of time. From our perspective, photons wander across the universe for unimaginable ages. But along the path of the photon itself, the start and the finish lie right next to each other. Two events that appear separated by billions of years in our history are, in a deeper sense, neighbours in the geometry of space-time. The star that emitted the photon and the eye that finally absorbs it are connected by a path through the universe where no time passes at all. It is a strange and beautiful idea. Light, the fastest thing that exists, crosses the largest distances imaginable, while carrying no sense of duration along the way. And to understand why this happens, we must begin by asking a deceptively simple question. What is time, really? When we say that something takes time, what do we really mean? It is a question that sounds philosophical at first, but physicists approach it in a surprisingly practical way. Rather than debating what time might be in some abstract sense, they ask a simpler question. How do we measure it? And the answer, in every case, involves a clock. But a clock is not a magical device that captures time itself. A clock is simply a system that repeats the same process over and over again with great regularity. If you look at a traditional pendulum clock, the process is easy to see. A weight swings gently back and forth, tracing the same arc again and again. Each swing becomes a tick. Each tick becomes a small step forward in time. Other clocks rely on different rhythms. A quartz watch contains a tiny crystal that vibrates when electricity passes through it. The crystal oscillates thousands of times each second, and electronics quietly count those vibrations. Even more precise clocks use atoms themselves. Inside an atomic clock, certain atoms switch between two energy states at an extraordinarily stable rate. The oscillations are so regular that modern atomic clocks can keep time so accurately that they would lose less than a second over millions of years. Yet despite these differences, every clock works according to the same basic idea. A process repeats. The repetitions are counted, and the count becomes what we call time. Seen this way, time is not something floating invisibly in the background of the universe. Time is the accumulation of physical change. If the processes inside a clock slow down, then the passage of time for that clock slows down as well. This idea may seem simple, but it carries an important implication. Time is always local. Each object carries its own clock, defined by the physical processes happening within it. Your heartbeat marks time inside your body. Electrical signals in your brain mark time in your thoughts. The chemical reactions inside your cells unfold in steady rhythms that quietly count the moments of your life. All of these processes together form what we might call your personal clock. Now, imagine something curious. Suppose you and a friend each hold an identical clock. Both clocks are perfectly synchronized. As you stand together, each second that passes for you also passes for your friend. The two clocks agree completely. Nothing seems unusual, but now suppose your friend climbs aboard a spacecraft and begins traveling through space at a very high speed. From your friend's perspective, everything continues normally. The clock on the spacecraft ticks steadily. 1 second follows another. Life aboard the ship feels ordinary, but from your perspective, watching the spacecraft speed away into the distance, something subtle changes. The moving clock appears to tick more slowly. Each second for the traveller stretches slightly longer than a second for you. At first, the difference would be incredibly tiny. At the speeds of everyday life, the effect is far too small to notice. If someone flies across the world on an airplane, the difference in elapsed time might be measured in billionths of a second. But with extremely precise atomic clocks, scientists have measured exactly this effect. Clocks carried aboard fast aircraft and satellites return showing slightly less elapsed time than clocks that remained on the ground. The moving clocks truly tick more slowly. This phenomenon is called time dilation, and it is one of the central discoveries of Einstein's theory of special relativity. What makes it so fascinating is that nothing about the clock itself is broken or altered. The gears still turn normally. The atomic oscillations continue as they always have. From the perspective of the traveller, their clock behaves perfectly. The difference arises not from the clock, but from the structure of space and time themselves. To understand why motion affects time, we must first notice something deeply unusual about light. In everyday life, speeds behave in a very simple way. If you throw a ball forward while standing still, the ball moves at some speed relative to the ground. If you throw the same ball while riding on a fast train, the speed of the ball relative to the ground becomes the speed of the train plus the speed of the throw. Speeds add together. This is what we naturally expect. But light refuses to follow this rule. No matter how fast you move, the speed of light remains the same. Imagine shining a flashlight while standing still. The beam of light travels outward at the speed of light, which is roughly 300,000 kilometers every second. Now imagine boarding a spacecraft moving at half that speed. If you shine the same flashlight forward, common sense might suggest that the beam should move faster relative to the outside world. But it does not. the light still travels at exactly the same speed, 300,000 kilometers each second. Not faster, not slower, the same speed for every observer. This strange fact has been confirmed by countless experiments. No matter how fast the source of the light is moving, and no matter how fast the observer is moving, the measured speed of light remains constant. When physicists first realized this, it seemed deeply puzzling. Something about our understanding of motion had to change. Einstein recognized that the only way to make sense of this behavior was to rethink our assumptions about space and time. If the speed of light is fixed for everyone, then the universe must adjust something else in order to keep that speed constant. And the thing that changes is time itself. Time stretches and compresses depending on how objects move. The faster something travels through space, the more slowly its internal processes unfold. Its clock ticks more slowly. Its time flows differently. At first, this may feel like an abstract idea, but it leads to a powerful new way of thinking about motion. Instead of imagining motion only through space, physicists began to see motion as happening through something larger, a four-dimensional structure called spacetime. In this deeper picture, distance and duration are woven together into a single fabric. Objects do not simply move across space, they travel along paths through space-time. And it turns out that every object in the universe is always moving through this fabric in its own way. Some of that motion goes into movement through space, some of it goes into movement through time, and as we will soon discover, the balance between those two kinds of motion explains why fast motion through space inevitably slows the passage of time. The story becomes even more surprising when we follow that idea all the way to its ultimate limit. Because when motion through space reaches the greatest speed the universe allows, something remarkable happens. Time itself comes to a halt. Imagine once again those two identical clocks sitting side by side on a quiet table. Their ticking is perfectly synchronized. 1 second passes for one clock, and 1 second passes for the other. If you were to watch them long enough, you would see that their hands move together in flawless agreement. This is what we expect from time. It feels universal and dependable. When two clocks start together, we naturally assume they will stay together, but the universe has a subtle surprise waiting for us. Let us take one of those clocks and place it aboard a spacecraft. The spacecraft leaves Earth and begins to travel faster and faster, moving far out into space. At first, nothing seems unusual. The clock inside the spacecraft ticks exactly as it always has. If an astronaut glances at it, each second feels perfectly ordinary. Their heartbeat continues at its usual rhythm. Their thoughts come and go in familiar patterns. A minute feels like a minute. Life aboard the ship feels completely normal. But from the perspective of someone watching from Earth, something remarkable begins to happen. The clock aboard the spacecraft appears to tick more slowly. Each second on that clock stretches slightly longer compared with the seconds measured by clocks on Earth. This is not a trick of vision. It is not caused by mechanical damage or faulty instruments. It is a genuine physical difference in how time unfolds. Physicists call this effect time dilation. The faster an object moves through space, the more slowly time passes for that object when compared with someone who remains still. At the gentle speeds of everyday life, the difference is so small that we never notice it. Commercial airplane crossing the sky moves quickly by human standards, yet even that speed produces only a tiny shift in time. However, with extremely precise instruments, scientists have measured the effect directly. In one famous experiment, atomic clocks were placed aboard airplanes and flown around the world. When the aircraft returned, the clocks were compared with identical clocks that had remained on the ground. The clocks that travelled showed slightly less elapsed time. They had aged just a tiny fraction less than their partners on Earth. The difference was incredibly small, far too small for a person to feel. But it was exactly what Einstein's equations predicted. The universe had quietly stretched time for the moving clocks. To see why this happens, it helps to think about motion in a slightly different way. In everyday language, we say that something moves through space. A car travels along a road, a bird flies across the sky, a spacecraft crosses the darkness between planets. But modern physics suggests that this description is incomplete. Instead of moving only through space, everything in the universe moves through spacetime. Spacetime is the combined fabric of space and time woven together into a single structure. Imagine it as a vast landscape where every path contains both distance and duration. When an object travels through space-time, some of its motion goes into changing position in space, and some of its motion goes into advancing through time. One way to picture this is to imagine that every object has a fixed motion budget. You can spend that budget moving through space, or you can spend it moving through time. But the total amount is limited. If you remain still in space, all of your motion goes into moving through time. Your internal processes unfold at their maximum pace. Your clock ticks normally, but if you begin to move through space, some of your motion budget shifts in that direction, and because the total is fixed, there is slightly less left over for motion through time. Your clock ticks a little more slowly. This idea might seem abstract at first, but it becomes clearer with a simple analogy. Imagine you are walking across an open field. You can walk straight north, straight east, or somewhere in between. But your total walking speed remains the same. If you walk entirely north, all of your motion goes into moving northward. You make no progress toward the east. If you walk entirely east, the opposite is true. But if you walk northeast, your movement divides between the two directions. You move partly north and partly east, but less in each direction than if you had walked in only one. Space-time behaves in a similar way. Motion through space and motion through time are like two directions in this larger landscape. If you move faster through space, some of your motion shifts away from time. As a result, time passes more slowly for you. This effect becomes dramatic when speeds grow very large. Imagine a spacecraft traveling extremely fast, approaching the speed of light. At 90% of the speed of light, time aboard the spacecraft flows noticeably slower than on Earth. A clock aboard the ship might tick only half as quickly as clocks on the ground. Push the speed even higher, closer to the cosmic speed limit set by light itself, and the effect becomes more extreme. Time slows further and further. Seconds stretch longer. Processes unfold more slowly. From the traveller's perspective, everything remains perfectly normal. Their own clock always ticks at the familiar rhythm of 1 second per second. But observers outside the spacecraft would see their entire world unfolding in slow motion. This strange behaviour is not a malfunction of clocks or an illusion of perspective. It is built into the structure of spacetime itself. Every object carries its own measure of time, determined by the path it takes through the universe. And the faster that path moves through space, the more gently time flows along it. This gradual slowing of time continues as speeds increase. Closer and closer to the speed of light, clocks slow further and further. And when we finally reach the ultimate limit, the speed at which light itself travels, something extraordinary happens. The entire motion budget shifts into space. Nothing remains for time. The clock stops. Time, at least along that path, no longer advances at all. This is why light occupies such a special place in the story of the universe. It moves at the one speed where the passage of time disappears completely. And to truly see how this works, physicists invented a beautifully simple thought experiment involving nothing more than mirrors and a pulse of light. For most of human history, motion seems simple. If you ride in a moving car and toss a ball forward, the ball moves faster relative to the ground than if you had thrown it while standing still. The speed of the car adds to the speed of the throw. This feels obvious because it happens around us all the time. If a train moves quickly down a track and someone inside throws a ball toward the front of the train, a person watching from the station sees the ball moving faster than the throw alone. These speeds combine naturally. For centuries, scientists assumed that light should behave the same way. Imagine standing on a quiet field at night and switching on a flashlight. The beam of light travels outward at an extraordinary speed, about 300,000 kilometers each second. That is fast enough to circle the entire Earth more than 7 times in a single second. Now imagine boarding a powerful spacecraft that moves through space at half that speed. If you point the same flashlight forward and turn it on, intuition suggests that the beam should move even faster relative to someone watching from Earth. After all, your motion should add to the motion of the light. But this is where the universe surprises us. Experiments show that the light does not move faster. It still travels at exactly the same speed, about 300,000 kilometers every second. No matter how fast the source moves, no matter how fast the observer moves, the speed of light remains constant. This discovery puzzled scientists deeply in the late 19th century. Physicists tried to measure small changes in the speed of light caused by Earth's motion through space, but again and again they found the same result. The speed of light never changed. One of the most famous experiments investigating this mystery was performed by Albert Michelson and Edward Morley in the 1880s. Their goal was to detect tiny differences in the speed of light depending on the direction it travelled. If Earth were moving through some invisible medium filling space, light moving along Earth's direction of motion should behave slightly differently from light moving across it. But the experiment found no difference at all. Light always travelled at the same speed. This result seemed impossible to reconcile with the ordinary rules of motion. For years, physicists struggled to explain it. Then, in 1905, Albert Einstein proposed a radical idea. He suggested that the speed of light is not simply the speed of a particular kind of motion. Instead, it is a fundamental property of the universe. The speed of light is the same for all observers, regardless of how they move. This idea may sound simple, but its consequences are extraordinary. Every observer must measure the same speed of light, then space and time themselves cannot remain fixed and universal. Something has to adjust in order to keep the speed of light constant, and the things that adjust are distance and duration. Lengths change slightly depending on motion. Time flows at different rates for different observers. Together, these effects ensure that everyone measures the same speed of light. At first, this may seem backwards. Instead of light changing speed, the universe changes the way space and time behave. But experiments have confirmed this strange conclusion again and again. The speed of light acts like a cosmic speed limit, woven into the structure of reality itself. Nothing with mass can exceed this speed, and anything that has no mass must travel exactly at this speed. Light is made of tiny particles called photons. Photons have no mass, so they move at the maximum speed allowed by nature. Other massless phenomena follow the same rule. Ripples in spacetime known as gravitational waves also travel at the speed of light. In a sense, the speed of light is not merely about light. It is the ultimate speed limit for the entire universe. Once Einstein accepted this constant speed as a fundamental fact, he realized something remarkable. If the speed of light is the same for everyone, then observers moving relative to one another must disagree about measurements of space and time. Two observers moving differently may measure different distances. They may measure different durations, yet both will still measure the same speed for light. This realization led to the theory now known as special relativity. One of the simplest ways to understand the consequences of relativity is to think again about motion through space-time. Earlier we imagined that every object has a certain amount of motion available, something like a limited budget. That motion can be spent moving through space, or it can be spent moving through time. The total amount remains constant. Light represents the extreme case. Photons move through space at the maximum possible speed. They use the entire motion budget travelling through space. There is nothing left for motion through time. That is why time does not pass along the path of light. From our perspective, photons may travel enormous distances. They may cross galaxies, wander through cosmic voids, or curve around massive clusters of galaxies under the influence of gravity. Their journeys can last millions or billions of years according to our clocks. But along the path of the photon itself, something very different happens. The beginning and the end of the journey lie right next to each other in space-time. No time accumulates between them. It is as though the photon leaves a distant star and arrives at your eye in a single moment. This idea can feel unsettling at first. Our everyday experience tells us that time always flows forward at the same pace. Yet the behavior of light reveals that time is more flexible than we once imagined. Time stretches and compresses depending on motion. The faster an object moves through space, the more gently its internal clock advances, and when motion through space reaches the ultimate speed limit, the speed of light, time itself falls silent. This discovery reshaped physics in the 20th century and continues to influence our understanding of the cosmos today. But the idea becomes even clearer when we explore a beautifully simple thought experiment involving mirrors and a pulse of light. With nothing more than those ingredients, physicists can demonstrate exactly why moving clocks must slow down. For most of human history, people believed that time flowed the same way everywhere. A second was a second for everyone. Whether you were standing still, riding a horse, or sailing across an ocean, time seemed to pass at exactly the same rate. It felt as though the universe contained an invisible master clock quietly ticking in the background. Every event in the cosmos, every heartbeat, every sunrise, every falling leaf would simply follow the rhythm of that universal clock. This idea feels natural because our everyday experiences happen at relatively slow speeds. Cars, airplanes, and even rockets move far more slowly than the speed of light. In that familiar world, time appears steady and dependable. But the strange behavior of light forced scientists to reconsider this comforting picture. If the speed of light is always the same for every observer, then the universe cannot keep both space and time fixed at the same time. Something has to bend. Einstein realized that the thing that bends is time itself. Imagine two observers moving relative to each other. Perhaps one stands on Earth while the other travels through space in a fast spacecraft. Both observers shine a beam of light and measure its speed. According to Einstein's insight, both must measure exactly the same value. The light travels about 300,000 kilometers every second for each of them. If both observers measure the same speed for light, yet they are moving differently, then their measurements of distance and time cannot both agree. The only way to keep the speed of light constant is for space and time to adjust. Distances may appear slightly shorter for moving objects, and time itself may flow more slowly. These effects are not illusions caused by faulty instruments or perspective. They are real physical features of space-time. This idea transforms our understanding of the universe. Instead of imagining space as a rigid stage where events unfold and time as a universal river flowing steadily through it, relativity shows that space and time are woven together. They form a single, flexible fabric. Physicists call this fabric spacetime. Every event in the universe occurs at a particular location in space and at a particular moment in time. In space-time, these two aspects cannot be separated completely. They are intertwined like threads in a woven cloth. When objects move through the universe, they follow paths through this four-dimensional landscape. Some of that motion carries them through space, some of it carries them through time. The balance between those two kinds of motion determines how quickly their clocks tick. To picture this, it can help to imagine motion as something that must be divided between two directions. Consider again the idea of a traveller walking across a wide open plain. Suppose the traveller moves at a steady pace, always covering the same total distance every hour. If they walk straight north, all of their motion goes toward the north. If they walk straight east, all of their motion goes toward the east. But if they walk northeast, their movement splits between the two directions. They move partly north and partly east, though not as far in either direction as if they had chosen just one. Spacetime behaves in a similar way. Every object has a certain total amount of motion through spacetime. That motion can be directed through space, through time, or some combination of both. When an object remains still in space, all of its motion flows through time. Its internal processes, heartbeats, chemical reactions, vibrations inside atoms, unfold at their maximum rate. But when the object begins to move through space, some of its motion shifts in that direction. Because the total remains fixed, less motion remains available for movement through time. Time slows down. The faster an object travels through space, the less motion remains for time. Its internal clock ticks more slowly. This idea may sound unfamiliar, yet it offers a gentle way to understand the strange behaviour of time dilation. Rather than imagining time stretching or compressing mysteriously, we can picture motion simply being shared between two directions within space-time. At ordinary speeds, the shift is extremely small. A person walking across a room redirects only the tiniest fraction of their motion away from time. Their clock slows by such a tiny amount that it would take unimaginably precise instruments to detect it. Even a jet aircraft flying around the world changes the rate of time only slightly. But when speeds become enormous, approaching the speed of light, the effect becomes dramatic. More and more motion flows into space. Less and less remains for time. A spacecraft travelling at 90% of the speed of light would experience time flowing much more slowly than clocks on Earth. A journey that feels like a year to the traveller might correspond to several years passing on the planet they left behind. Push the speed even closer to the cosmic limit set by light, and time slows even further. Eventually we reach the ultimate boundary. At the speed of light itself, every bit of motion is directed through space. Nothing remains for time, and that is why the passage of time disappears completely along the path of light. Photons move through space at the maximum speed allowed by the universe. They use the entire capacity of motion within space-time travelling through space. With no motion left for time, their internal clock, if such a clock could exist, would remain frozen. This insight is one of the most beautiful consequences of Einstein's theory. The universe no longer contains a universal clock governing everything. Instead, each object carries its own measure of time, shaped by the path it follows through space-time. Two travellers moving differently may age at different rates. Two clocks following different journeys through the universe may record different amounts of time. Yet the laws of physics remain consistent for all observers. And at the heart of this strange new picture lies a constant beacon, the speed of light, the cosmic limit that shapes the very structure of space and time. To see how these ideas become precise and measurable, physicists often turn to a wonderfully simple device built from mirrors and a bouncing pulse of light. This thought experiment reveals with quiet elegance exactly why moving clocks must slow down. To understand why moving clocks run more slowly, physicists often imagine a very simple clock. It is not made of gears or springs. It does not tick with pendulums or vibrating crystals. Instead, this clock uses nothing more than a single beam of light and two mirrors. Picture two perfectly polished mirrors facing one another, separated by a small distance. Between them, a tiny pulse of light travels back and forth. The light leaves the lower mirror, rises upward, strikes the upper mirror, and reflects back down again. Each time the light completes one full round trip, up and then down, the clock records one tick. This device is known as a light clock. It may sound like a toy, but it captures something very important about how time is measured. Every clock in existence ultimately depends on some repeating physical process. A pendulum swings. Quartz crystal vibrates. At the most precise level, atomic clocks measure tiny oscillations inside atoms. These repeating motions define what we call seconds. The light clock simply replaces those mechanisms with a motion of light itself. Now imagine that this light clock is sitting quietly on a table. The beam of light travels straight up and straight down between the mirrors. The distance is fixed, and the speed of light is constant, so the time between ticks remains perfectly steady. If the mirrors are 1 meter apart, the light must travel 2 meters during each full tick, 1 meter upward and 1 meter downward. Since light moves about 300,000 kilometers each second, the round trip happens extremely quickly. But the important point is that the timing remains consistent. Tick, tick, tick. Now let us gently set the entire clock in motion. Imagine placing this light clock inside a spacecraft gliding smoothly through space. To someone inside the spacecraft, the clock behaves exactly as before. The light travels straight up and down between the mirrors. Tick, tick, tick. Nothing seems different at all. But now consider what an observer outside the spacecraft sees. From their perspective, the spacecraft is moving sideways while the light travels between the mirrors. This means the beam of light no longer moves straight up and down. Instead, the light follows a diagonal path. As the spacecraft moves forward, the light must travel slightly forward as well in order to reach the upper mirror. On the way back down, it again travels diagonally to meet the lower mirror as the ship continues moving. If we were to trace the path of the light from the outside observer's perspective, it would form a zigzag pattern, like a series of tiny triangles. And here is the key insight. The diagonal path is longer than the vertical path. The light must travel a greater distance to complete each tick of the clock. But the speed of light cannot change. Light always travels at the same speed, about 300,000 kilometers each second, no matter who measures it. If the distance increases but the speed stays fixed, then the time required must increase as well. The tick of the moving clock takes longer. From the outside observer's perspective, the moving clock runs more slowly. Tick, pause, tick, pause. Each tick stretches slightly longer than it did before. This simple thought experiment reveals the heart of time dilation. The slowing of time is not a mysterious illusion or a trick of perception. It follows naturally from two simple facts. First, the speed of light is always the same. Second, moving observers see the path of light stretch into longer diagonals. Those two ideas together mean that moving clocks must tick more slowly, and the faster the clock moves, the longer the diagonal path becomes. The effect grows stronger as speed increases. If the spacecraft moves faster, the zigzag path of the light stretches even further, sideways. Each tick requires the light to travel a longer distance. The clock slows further. Physicists can express this relationship with a mathematical factor, often called the relativistic stretching factor. In written form, the idea is sometimes represented by a symbol called gamma. Gamma describes how much time stretches for an object moving at a particular speed. The rule says that gamma equals 1 divided by the square root of 1 minus the square of the object's speed divided by the square of the speed of light. When the speed is very small compared with the speed of light, this factor remains very close to 1. Time flows almost normally. But as the speed grows closer to the speed of light, the number increases dramatically. Gamma becomes larger and larger. And as the speed approaches the speed of light itself, the factor grows without limit. In simple terms, time slows more and more. For something moving extremely close to the speed of light, time nearly stops. This mathematical expression is simply a precise way of describing what the light clock already showed us. When motion causes light to follow longer paths, clocks must tick more slowly. The idea works for any type of clock: a pendulum clock, a quartz wristwatch, an atomic clock inside a laboratory, even the biological rhythms inside your own body. Every physical process depends on the flow of time along its path through space-time. If motion through space changes that flow, every process slows together. This means that a traveller moving extremely fast would experience time differently from someone who remained behind. Their clocks would tick more slowly, their aging would unfold more gently, and their journey through the universe would follow a slightly different rhythm of time. The light clock thought experiment reveals this truth with quiet elegance. By imagining nothing more than a beam of light bouncing between two mirrors, we discover that time itself must stretch whenever motion through space becomes significant. And when that motion approaches the ultimate speed of light, the stretching becomes so extreme that the passage of time fades away entirely. Which brings us to an even deeper question. If time slows more and more as speed increases, what happens at the exact speed of light itself? Up to this point, we've explored the strange slowing of time using ideas and images. We imagine clocks travelling through space, beams of light bouncing between mirrors, and the quiet stretching of time as motion grows faster. But physicists eventually wanted something more precise than imagery alone. They wanted a way to calculate exactly how much time slows when an object moves at a particular speed. To do this, they developed a mathematical relationship that describes the connection between motion and time. At the heart of that relationship is a quantity often called the relativistic stretching factor. Physicists usually refer to it by a short Greek letter called gamma, but you can think of gamma simply as a number that tells you how much time stretches for a moving object. When an object is completely still relative to you, gamma equals 1. That means time flows normally. A second for the moving object matches a second for you. But as the object begins to move faster, gamma becomes slightly larger than 1, and that is when time begins to stretch. To see how this works, imagine a spacecraft gradually increasing its speed. At first, the change is almost invisible. Suppose the spacecraft moves at 10% of the speed of light. That may sound extraordinarily fast by human standards, but compared with the light, it is still relatively slow. At this speed, the stretching factor is only a tiny bit larger than 1. Time aboard the spacecraft slows by such a small amount that it would take extremely precise clocks to detect the difference. Now imagine increasing the speed further. Perhaps the spacecraft reaches half the speed of light. Now the stretching becomes noticeable. Time aboard the spacecraft begins to move significantly more slowly compared with clocks on Earth. A traveller might experience 10 hours passing aboard the ship while observers on Earth measure slightly more. Push the speed even further to 90% of the speed of light, and the effect becomes dramatic. At that velocity, the stretching factor becomes a little more than 2. This means that time aboard the spacecraft flows at less than half the rate measured by someone who remains at rest. If a traveller experiences 1 year aboard the ship, more than 2 years may pass for those waiting back on Earth. Increase the speed again, to 99% of the speed of light, and the effect becomes even more astonishing. Now the stretching factor grows to roughly 7. A single year experienced by the traveller would correspond to about 7 years passing for the stationary observer, and if the spacecraft could somehow move even closer to the speed of light, 99.9% of that speed, the stretching factor would grow to around 22. 1 year aboard the spacecraft would match more than 2 decades on Earth. Each small step closer to the cosmic speed limit causes the stretching of time to grow more and more extreme. And this behaviour is not random. It follows a very specific mathematical pattern. Physicists describe the relationship this way. The stretching factor equals 1 divided by the square root of 1 minus the square of the object's speed divided by the square of the speed of light. Although that sentence may sound complicated at first, its meaning is actually quite simple. The formula compares 2 things: how fast the object is moving and how fast light moves. When the object's speed is much smaller than the speed of light, the fraction inside the equation remains tiny. As a result, the stretching factor stays very close to 1. Time behaves almost normally, but as the object's speed approaches the speed of light, that fraction grows larger and larger. The quantity inside the square root becomes smaller and smaller, and the stretching factor grows dramatically. In other words, time slows more and more. If we imagine pushing the speed closer and closer to the speed of light, something remarkable happens. The stretching factor does not merely grow large, it grows without limit. The mathematics predicts that it increases toward infinity. In practical terms, this means that time slows more and more dramatically as an object approaches the speed of light. Seconds stretch longer, processes unfold more slowly. From the perspective of a stationary observer, everything aboard the fast-moving spacecraft seems to happen in slow motion. Yet from the traveller's own perspective, nothing unusual occurs. Their clocks tick normally, their heartbeat remains steady. Their thoughts flow at their familiar pace. This difference between perspectives is one of the deepest lessons of relativity. Time does not belong to the universe as a single shared river. Instead, each observer carries their own measure of time, shaped by the path they follow through space-time. And the mathematics behind relativity allows us to predict exactly how those different clocks will compare. The closer an object moves to the speed of light, the more its time stretches relative to observers moving more slowly. Eventually, we reach a profound conclusion. If an object could somehow reach the speed of light itself, the stretching factor would grow infinitely large. Time would slow to a complete halt. Of course, this raises an immediate and fascinating question. If approaching the speed of light causes time to slow so dramatically, why do ordinary objects, like spacecraft, planets, or people, never reach that ultimate speed? Why does the universe allow objects to approach the speed of light, yet never quite touch it? To understand that mystery, we must explore another, surprising consequence of relativity: the enormous energy required to accelerate massive objects as they approach the cosmic speed limit. By now we've seen that time stretches dramatically as motion approaches the speed of light. The faster something moves, the more slowly time passes along its path through the universe. But this raises a natural question. If moving faster slows time, why not simply keep accelerating forever? Why can't a spacecraft, given enough fuel and enough patience, eventually reach the speed of light itself? At first glance, it might seem possible. After all, we know how acceleration works in everyday life. Press the accelerator in a car and the car speeds up. Apply more force and it moves even faster. It feels as though speed can increase without limit. But the universe quietly imposes a boundary. As objects move faster and faster, approaching the speed of light, accelerating them becomes increasingly difficult. Each small increase, in speed requires more and more energy, and the closer an object gets to the speed of light, the more dramatic this effect becomes. To understand why, it helps to think about how energy and motion are connected. In everyday physics, we often describe motion using a quantity called kinetic energy. This is the energy associated with movement. A rolling ball has kinetic energy. A moving car has kinetic energy. A spacecraft gliding through the darkness between planets carries kinetic energy as well. At ordinary speeds, kinetic energy increases smoothly as speed increases. If you double the speed of a car, its kinetic energy grows larger, but remains manageable. But as speeds approach the speed of light, the relationship between energy and motion changes. Relativity tells us that accelerating an object requires increasing amounts of energy, not only because the object moves faster, but because the very structure of spacetime resists further acceleration. One way physicists describe this effect is by saying that the object's relativistic inertia grows. This does not mean that the object literally gains more mass in the everyday sense. Instead, it means that the energy required to push the object faster grows dramatically as its speed approaches the cosmic limit. Imagine trying to push a heavy sled across a frozen lake. At first the sled moves easily. A small push sends it sliding forward. But suppose the sled somehow becomes heavier with every meter it travels. The farther it moves, the harder it becomes to push. Eventually the sled becomes so heavy that no matter how hard you push, it barely accelerates at all. Something similar happens when an object approaches the speed of light. At lower speeds, a rocket engine can accelerate a spacecraft relatively easily. Each burst of thrust adds more speed, but as the spacecraft moves faster and faster, each additional increase requires far more energy than the last. The amount of energy needed grows rapidly, and as the spacecraft approaches the speed of light, the required energy grows without bound. In mathematical language, physicists say that the energy required tends toward infinity. In plain language, it means that no finite amount of energy can push a massive object all the way to the speed of light. The closer the object gets to that speed, the harder it becomes to go even a little faster. Reaching the speed of light would require an infinite amount of energy, and infinite energy is not something the universe appears willing to provide. This limitation applies to anything that possesses mass. Electrons have mass, protons have mass, spacecraft, planets, and people all have mass. Because of that, they can approach the speed of light but never actually reach it. They can move incredibly fast, perhaps 90% of the speed of light, or even 99%, but the final step to light speed always remains out of reach. Light itself, however, is different. Photons, the particles that make up light, have no mass. Because they are massless, they do not face the same restriction. Instead of needing energy to reach the speed of light, photons simply exist at that speed. They cannot move slower, they cannot move faster, they always travel at the same cosmic pace, about 300,000 kilometers every second. In a sense, the universe treats the speed of light not as a speed that objects gradually climb toward, but as a special state reserved for massless particles. Anything with mass must remain below that limit. Anything without mass must travel exactly at that speed. This rule forms one of the most important boundaries in all of physics. It ensures that the speed of light acts as a universal speed limit. No signal, no particle carrying information, and no object with mass can outrun it. That limit shapes the structure of the cosmos. It governs how galaxies interact, how signals travel through space, and how cause and effect unfold across the universe. And it leads to one of the most astonishing consequences of relativity. Because photons always travel at the speed of light, and because time slows more and more dramatically as objects approach that speed, the passage of time along the path of light disappears completely. For objects with mass, time can slow dramatically but never quite stop. For light itself, time does not flow at all. The journey of a photon through the universe takes no time from its own perspective. To us, a photon may travel across billions of years. It may leave the surface of a distant star, wander through the vast darkness between galaxies, and eventually reach a telescope on Earth. But along the photon's own path through space-time, those two events, emission and arrival, sit right next to each other, separated by distance, yet not separated by time. Understanding this strange idea requires one final concept. We must look more closely at what physicists mean when they speak about the proper time experienced along a path through space-time. Imagine again a photon leaving the surface of a distant star. Perhaps that star lies hundreds of light years away, or perhaps it shines from the far edge of our galaxy, tens of thousands of light years across the dark ocean of space. From our perspective here on Earth, the photon begins an incredibly long journey. It travels through clouds of gas and dust. It slips past wandering planets. It crosses vast regions of empty space, where even a single atom might be separated from its neighbour by kilometres. Second after second passes, minute after minute, year after year. If the photon comes from a distant galaxy, the journey may last millions or even billions of years according to the clocks we use on Earth. But now let us try to imagine the story from the photon's perspective. This is where the universe becomes truly strange. To understand it, physicists introduce a concept called proper time. Proper time simply means the time experienced along a particular path through space-time. It is the time measured by a clock travelling alongside an object. If you wear a wristwatch while walking through a park, the time shown on that watch is your proper time. If an astronaut carries a clock aboard a spacecraft, the ticking of that clock measures the proper time along the spacecraft's journey. Every traveller in the universe carries their own measure of proper time, determined by the path they follow through space-time. For objects moving slowly, proper time behaves exactly as we expect. If two people stand together and synchronize their watches, their clocks tick at the same pace. Their proper times match perfectly. But as motion grows faster and faster, relativity begins to reshape this picture. When an object moves rapidly through space, its proper time slows relative to observers who remain still. This is the time dilation we explored earlier. A fast-moving astronaut ages slightly more slowly than someone on Earth. Their internal processes unfold more gently along their path through space-time. Yet even in these extreme situations, time still flows for the traveller. Their clock never stops completely. Even at speeds extremely close to the speed of light, a traveller still experiences moments passing one after another. But photons are different. Photons move at the speed of light itself, and when physicists apply the mathematics of relativity to that speed, something extraordinary appears. The proper time along the path of a photon becomes zero. In other words, the amount of time experienced along the photon's journey is exactly nothing. From the perspective of space-time geometry, the photon's departure and arrival are connected by a path that contains no elapsed time. This does not mean the photon somehow feels frozen in time. In fact, the idea of a perspective belonging to a photon is not entirely meaningful. Because time does not pass along its path, a photon cannot carry a clock or observe events unfolding. Still, the mathematics reveals something remarkable about the structure of space-time. Along the path travelled by light, the interval of time measured by any possible clock travelling with the photon would be zero. This is what physicists mean when they say that photons experience zero proper time. To us, the photon may have crossed enormous distances. Imagine a photon that left a galaxy 10 billion years ago. During its journey, entire generations of stars may have formed and died. Galaxies may have collided and reshaped themselves. Life on Earth evolved from simple organisms into complex ecosystems. All of that unfolded during the photon's long voyage across the cosmos. Yet along the photon's path through space-time, none of that time accumulates. The event where the photon is emitted and the event where it is absorbed are separated by distance but not by proper time. They lie on the same light-like path. If we were able to trace that path through the four-dimensional fabric of space-time, it would connect the two events without any passage of time along the way. This idea challenges our everyday intuition. We're used to thinking of time as something universal, something that flows steadily from past to future. But relativity teaches us that time depends on the path taken through space-time. Different journeys through the universe accumulate different amounts of proper time. A person walking slowly through a park experiences one flow of time. An astronaut travelling close to the speed of a light experiences a slightly slower flow. And light itself follows a path where the passage of time vanishes entirely. The photon's journey becomes a bridge between distant events in the universe. From our perspective, the bridge stretches across enormous distances and unimaginable spans of time. But from the geometry of space-time itself, the path contains no time at all. Emission and absorption become neighbours along that light-like connection. The star that released the photon and the eye that receives it are joined by a path where time does not accumulate. And this curious feature of space-time leads us toward an even deeper way of understanding the universe. To truly see why the photon's path behaves this way, physicists describe space-time using a geometric picture, one that reveals how different kinds of paths divide into categories. Some paths belong to objects moving slower than light, some belong to objects that could never exist, and some belong to light itself. The key to understanding these categories lies in a simple but powerful idea known as the space-time interval. To understand why light experiences no passage of time, it helps to step back and look at the universe in a slightly different way. Instead of imagining events unfolding in ordinary three-dimensional space, with time ticking separately in the background, physicists often picture the universe as a four-dimensional landscape. 3 dimensions describe where something's located, and 1 dimension describes when it happens. Together, these 4 dimensions form space-time. Within this landscape, every object traces a path. That path represents the entire history of the object, where it has been and when it was there. Physicists call this path a world line. If you were to draw your own world line, it would begin at the moment you were born and continue forward through every step of your life. Each place you have ever stood and each moment you have ever experienced would appear somewhere along that path. For objects moving slowly through space, their world lines rise mostly upward through time. Imagine a simple diagram. The horizontal direction represents space. The vertical direction represents time. An object that remains still in space moves only upward in the diagram. Its world line becomes a straight vertical line. Time flows steadily as the object remains in the same place. But now imagine an object that moves through space, perhaps a car travelling down a highway. In the space-time diagram, the car's path no longer rises straight upward. Instead, it tilts slightly to the side. As time passes, the car changes position in space, and its world line leans accordingly. The faster the object moves through space, the more its world line tilts. This way of drawing motion through space-time helps reveal something subtle. The amount of time experienced by an object depends on the shape of its path. Some paths accumulate more proper time, some accumulate less. An object that remains still in space follows a path that accumulates the greatest possible proper time between 2 nearby events. In contrast, an object moving rapidly through space follows a path that accumulates less proper time. That is why fast-moving clocks tick more slowly. Their world lines lean more strongly through the space-time diagram, and the geometry of space-time gives them less proper time along that path. Now let us imagine pushing this idea further. What happens to the world line of something moving faster and faster? As speed increases, the world line tilts more and more sideways. It begins to lean closer to the horizontal direction of space. But there is a limit to how far it can tilt. That limit corresponds to the speed of light. In a space-time diagram, the paths taken by light form lines that sit exactly at this boundary. These paths are neither purely vertical nor purely horizontal. They lie at a precise angle that represents motion at the speed of light. Physicists call these special paths light-like paths. Along a light-like path, something remarkable occurs. The space-time interval, the geometric quantity that determines proper time, becomes zero. In simple terms, the geometry of space-time says that no proper time accumulates along the path taken by light. That is why photons experience zero proper time. Their world lines lie exactly along the boundary that separates motion slower than light from motion that would be faster than light. Any object with mass must remain within that boundary. Its world line must stay inside the region where time continues to accumulate. Light alone moves precisely along the edge. To visualize this boundary, physicists sometimes imagine a structure called a light cone. Picture a cone of light spreading outward from a single flash. The flash occurs at a particular event in space-time. From that event, light travels outward in every direction. As time passes, the expanding sphere of light grows larger and larger. If we compress this picture into a space-time diagram, that expanding sphere forms the surface of a cone. The upper half of the cone represents all the places light could travel after the event. The lower half represents all the places light could have come from before the event. Anything inside the cone moves slower than light. Anything exactly on the surface of the cone moves at the speed of light. And anything outside the cone would require faster than light motion, which the laws of relativity do not allow. This geometric picture reveals something profound. The structure of space-time itself determines which events can influence one another. Signals and causes must travel within the boundaries defined by light. Nothing can move outside those limits, and because light travels exactly along the surface of this cosmic boundary, its path accumulates no proper time. From the perspective of space-time geometry, a photon's journey connects two distant events along the edge of the light cone. The star that emits the photon lies at one end of that path. The telescope that detects the photon lies at the other. The photon traces the boundary between past and future, linking those events across the vastness of space. To us, the journey appears incredibly long. Billions of years may pass between the moment the photon leaves a distant galaxy and the moment it arrives here on Earth. But along the photon's world line, the geometry of space-time assigns no proper time to the journey. Emission and absorption sit directly along the same light-like path, separated by space, but not by time. This elegant geometric view allows physicists to understand relativity not just as a collection of strange rules about clocks and motion, but as a deeper statement about the shape of the universe itself. Space-time has a structure. World lines trace paths through that structure, and the speed of light marks the boundary that separates different kinds of journeys through the cosmos. In the next part of our exploration, we will see how these paths through space-time lead to one of the most famous thought experiments in relativity. The story of two twins who age differently because they follow different journeys through the universe. Earlier, we introduced a quiet but powerful idea. Every object moving through the universe carries its own measure of time. Physicists call this proper time, but in gentler language you might think of it as your personal clock in the universe. This clock is not necessarily something you can hold in your hand. It does not have gears or glowing numbers. Instead, it is woven into the very processes that make up your existence, your heartbeat, the rhythm of your breathing, the electrical signals moving through your brain, the countless chemical reactions unfolding inside your cells. All of these processes advance according to the proper time along your path through space-time. And that path, your world line, determines how much time accumulates between events in your life. For most of us, moving slowly across the surface of Earth, the difference between our personal clock and anyone else's is extremely small. If two friends stand together and synchronize their watches, those watches will remain nearly identical even after years of living side by side. The speeds we experience in daily life are simply too small for relativity to produce noticeable changes. But when motion through space becomes enormous, the story begins to change. Imagine two astronauts beginning their journeys together. At the moment they depart, they stand side by side on a launch platform. Their clocks show exactly the same time. Then their paths through space-time begin to diverge. One astronaut remains on Earth. Their days unfold in familiar ways. They walk through cities, watch the seasons change, and observe the steady rhythm of life on a planet orbiting the Sun. Their world line rises gently upward through space-time, with only a slight tilt caused by Earth's motion around the Sun and the galaxy's slow drift through the Milky Way. The second astronaut boards a spacecraft capable of travelling at tremendous speed. Soon the ship accelerates to a velocity approaching the speed of light. From the astronaut's perspective, the journey feels ordinary enough. They float inside the quiet cabin of the spacecraft. They eat meals, read messages from home, and watch the stars slide slowly across the windows. Their personal clock ticks normally. A minute feels like a minute. An hour feels like an hour. Their body ages in the familiar rhythm of human life. But far away on Earth, something different unfolds. Because the astronaut spacecraft is moving so rapidly, the flow of proper time along their world line is slower than the flow of time along Earth's path. Observers on Earth see the spacecraft's clocks running more slowly. The traveller ages more gently. Years pass on Earth while fewer years accumulate along the astronaut's journey. This difference in aging is not a matter of perspective or illusion. It is a genuine physical effect. If the astronaut eventually returns to Earth, the difference becomes undeniable. The traveller may have aged only 10 years. Meanwhile, 20 or 30 years may have passed for the people who remained behind. This famous scenario is often called the twin paradox. Two twins begin with identical ages. One stays on Earth, the other travels through space at extraordinary speed. When the traveller returns, the twins are no longer the same age. The travelling twin is younger. The explanation lies entirely in the geometry of space-time. The two twins followed different paths through the universe. Those different paths accumulated different amounts of proper time. In space-time diagrams, the twin who stayed on Earth follows a nearly straight vertical path. The travelling twin follows a path that tilts outward as the spacecraft accelerates, then tilts back again during the return journey. Because of the way space-time geometry works, that tilted path contains less proper time. This idea may seem counterintuitive at first. We often imagine that the straightest path between 2 points is the shortest. But in space-time, the situation is reversed. For objects moving slower than light, the straight path through space-time actually produces the greatest amount of proper time. Any detour through space reduces the time experienced along the journey. That is why moving clocks run more slowly. Their world lines lean more strongly through space-time, and that geometric tilt shortens the proper time accumulated along the path. The twin paradox simply reveals this principle in a dramatic way. One twin's world line stays close to vertical. The other twin's path leans outward through space. When their journeys reconnect, the difference in accumulated time becomes visible. And this idea leads us back once again to the strange case of light. If an object moves extremely fast, its world line tilts strongly through space-time. Proper time shrinks. For astronauts travelling close to the speed of light, time slows dramatically. But photons move even faster, at the ultimate speed limit allowed by nature. Their world lines do not merely tilt, they lie exactly along the boundary of space-time where proper time disappears entirely. The geometry of space-time assigns zero proper time to those paths. In other words, the personal clock along the path of light never advances. From the photon's point of view, if such a viewpoint could exist, the moment of departure and the moment of arrival are joined without any passage of time between them. The universe connects distant places with bridges of light where time stands still, and those bridges define the very limits of how cause and effect spread through the cosmos. To understand that boundary more clearly, we now turn to one of the most important geometric structures in relativity, the light cone. Let us return once more to the story of the two twins. It is one of the most famous thought experiments in modern physics, not because it is complicated, but because it reveals something deeply surprising about the nature of time. Imagine two twins standing together on Earth. They are the same age. Their watches are synchronized down to the very last second. If you were to observe them at this moment, nothing about their situation would seem unusual. But their lives are about to follow very different paths through the universe. One twin remains on Earth. They continue living a familiar life, watching the slow turning of seasons, the rise and fall of civilizations, the quiet passage of years. Their world line through space-time is relatively simple. It rises steadily upward as time passes, with only slight tilts caused by Earth's motion around the Sun and the Sun's slow orbit around the centre of the Milky Way. The second twin chooses a far more adventurous journey. They board a spacecraft designed to travel at extraordinary speeds. Soon the engines ignite, and the spacecraft accelerates away from Earth, climbing closer and closer to the speed of light. At last, the ship reaches an incredible velocity, perhaps 99% of the speed of light. From the perspective of observers back on Earth, the spacecraft now moves so quickly that time aboard the ship begins to slow dramatically. Clocks on the spacecraft tick more slowly. Biological processes unfold more gently. The traveller ages at a reduced pace compared with people on Earth. But inside the spacecraft, the traveller experiences nothing unusual. The ship feels quiet and calm. Their clock ticks normally. If they glance at their wristwatch, each second arrives at the familiar rhythm they have always known. A minute still contains 60 seconds. An hour still contains 60 minutes. Their body does not feel as though it is slowing down. Their thoughts continue at the same pace. In relativity, this is an important idea. Every observer always experiences their own proper time normally. No traveller ever feels time stretching inside their own frame of reference. Now imagine that the spacecraft continues its journey for several years according to the traveller's clock. Eventually, the astronaut turns the ship around and begins the long journey back toward Earth. Again, the spacecraft travels at an extraordinary speed, and again, time aboard the ship flows more slowly compared with time on Earth. Finally, after many years of travel through space, the spacecraft returns home. The traveller steps out and reunites with their twin. But something remarkable has happened. The twin who remained on Earth is now much older. While the traveller experienced perhaps 10 years of life aboard the spacecraft, 20 or even 30 years may have passed on Earth. The two twins began the experiment at the same age. Yet when they meet again, their ages are different. The travelling twin has aged less. At first glance, this situation may seem puzzling. After all, relativity tells us that motion is relative. From the traveller's point of view, it might seem that Earth was moving away and then returning. Shouldn't the traveller then see Earth's clocks running slowly instead? Why does only the travelling twin end up younger? The answer lies in the geometry of the journeys themselves. The twin who remained on Earth followed a relatively smooth path through space-time. Their world line is nearly straight. The traveller, however, followed a more complex path. Their journey involved acceleration when leaving Earth, a long high-speed cruise through space, and another acceleration when turning around to return home. In space-time diagrams, this creates a world line that bends outward and then bends back again. Because of the geometry of space-time, that curved path accumulates less proper time. This means fewer seconds pass along the traveller's journey. The difference in aging is therefore not a paradox at all. It is simply the result of two travellers following different paths through the four-dimensional landscape of space-time. Each path accumulates its own amount of proper time, and the universe keeps track of those differences with perfect precision. In a quiet way, the twin paradox teaches us that time is not a universal river flowing the same way for everyone. Instead, time depends on the journey you take, through the universe. Different paths through space-time produce different amounts of lived time, and when we push this idea to its ultimate limit, we return once again to the strange case of light. Photons follow paths that lie exactly along the boundary of space-time's geometry. Their world lines trace the edges of light cones, the surfaces that separate what can influence an event from what cannot. Along those paths, the accumulated proper time is not merely small, it is zero. While travellers moving close to the speed of light experience greatly slowed time, light itself experiences none at all. The photon's journey from a distant star to your eye spans enormous distances. Yet the geometry of space-time connects those events with no proper time in between. The star emits the photon arrives, and along that light-like path, the universe records no ticking clock. To understand how these boundaries organize the flow of cause and effect throughout the cosmos, we must look more closely at the structure formed by those light-like paths. Physicists call this structure the light cone. Imagine a single flash of light appearing in the darkness of space. Perhaps a distant star suddenly brightens, or perhaps a small lamp is switched on in a quiet room. At the exact moment the light appears, it begins spreading outward in every direction. If you could watch this expansion from above, you would see a glowing sphere growing larger and larger as time passes. After 1 second, the light has travelled about 300,000 kilometres. After 2 seconds, it has travelled twice that distance. After a minute, the expanding sphere has grown enormous. And after years or centuries, the light has spread across vast regions of space. This simple idea, the outward spreading of light, turns out to reveal something very deep about the structure of the universe. To see why, physicists imagine compressing this expanding sphere into a space-time diagram. Instead of showing all 3 dimensions of space, we focus on just 1 dimension of space and 1 dimension of time. In this diagram, the moment when the flash occurs becomes a single point. Time moves upward. Space stretches sideways. As the light spreads outward, its expanding sphere traces a shape that widens as time increases. In the diagram, this shape becomes a cone. Physicists call it a light cone. The tip of the cone represents the moment when the flash of light occurred. The surface of the cone represents the path taken by light moving away from that event, and the region inside the cone represents everything that could possibly be affected by that flash of light. If you are located somewhere inside the cone, then light from the event can eventually reach you. But if you lie outside the cone, the light will never arrive, at least not without travelling faster than the speed of light, which the laws of physics forbid. This idea allows us to divide the universe into regions of influence. The upper half of the cone is called the future light cone. It contains every event that the original flash could possibly influence. If the light reaches a distant planet, warms a spacecraft, or strikes a telescope, Those events lie inside the future light cone. The lower half of the cone is called the past light cone. It contains every event that could have influenced the flash in the first place. Perhaps the star that emitted the light formed billions of years earlier. Perhaps a nuclear reaction inside its core triggered the flash. All of those earlier events lie within the past light cone. Anything outside the cone is separated in a different way. Those events are too far away in space for light, or any signal travelling at or below the speed of light, to connect them within the given time. They lie beyond the reach of cause and effect. This simple geometric picture reveals an extraordinary truth. The speed of light does more than describe how fast light travels. It defines the boundary of causality in the universe. Causality is the principle that causes come before their effects. A spark must occur before a flame appears. A message must be sent before it can be received. Light cones show us exactly which events can influence which others. Signals, forces, and information must travel within these cones. Nothing can cross from one event to another faster than light. If something could travel faster than light, it would move outside the boundaries of the light cone, and that would create strange possibilities. Effects could appear before their causes, messages could arrive before they were sent, the orderly structure of cause and effect could break down. Relativity prevents this by establishing the speed of light as an absolute limit. Every signal in the universe, every beam of light, every radio wave, every ripple of gravity must travel at or below this speed. This rule keeps the structure of spacetime consistent. It ensures that cause always precedes effect within each observer's frame of reference, and it reveals something subtle about the role of light itself. Light travels exactly along the surface of the cone, not inside it, not outside it, exactly along the boundary. Objects with mass move more slowly than light. Their world lines remain inside the cone. They accumulate proper time along their journeys. But light occupies the edge itself. The surface of the cone represents paths where the space-time interval contains no proper time at all. This is the same idea we encountered earlier when we spoke about photons experiencing zero proper time. The geometry of space-time assigns no elapsed time to paths that lie exactly along the surface of the light cone. Light connects distant events without any accumulation of time along the path. The star that emits a photon and the telescope that receives it are linked by one of these boundary paths. To us, the journey may take millions or billions of years, but in the language of space-time geometry, the two events sit along a light-light connection where no proper time passes. Light cones therefore reveal both the structure of causality and the strange timelessness of light. They show us that the universe is not merely a collection of objects drifting through empty space. Instead, it is a carefully organized network of events connected by signals that move through space-time at limited speeds. The speed of light defines the edges of that network, and along those edges the passage of time disappears. Understanding this structure brings us closer to the deeper meaning of the cosmic speed limit itself. Why does the universe insist that nothing travels faster than light? And how does that limit preserve the order of cause and effect across the vastness of the cosmos? Those questions lead us to the next step in our journey through relativity. By now, a quiet pattern has begun to emerge in our story. Again and again we encounter the same number, about 300,000 kilometers every second. This is the speed of light in empty space. At first it might seem like just another measurement, like the speed of sound in air or the speed at which a planet circles its star. But the speed of light is something very different. It is not merely the speed of a particular object, it is a fundamental property of the universe. In the theory of relativity, this speed plays a special role. It defines the maximum rate at which any influence can travel through space-time. No signal can outrun it, no message can exceed it. No object with mass can ever reach it. This universal limit shapes the structure of reality in ways both subtle and profound. To see why, imagine a simple situation. Suppose you send a message to a friend on a distant planet. The message travels as a beam of radio waves, which are simply another form of light. Because radio waves travel at the speed of light, the message cannot arrive instantly. It must take time to cross the distance. If the planet lies 1 light minute away, the message will arrive 1 minute after it is sent. If the planet lies 1 light year away, the message will arrive a full year later. This delay may seem inconvenient, but it preserves something very important. It ensures that cause always comes before effect. The message is sent first, then it is received. Now imagine a universe without this speed limit. Suppose signals could travel infinitely fast. In that strange universe, a message could arrive at its destination the very instant it was sent, no matter how far away the receiver might be. At first, this might seem convenient, but relativity reveals that such a universe would quickly become deeply confusing. Because motion is relative, two observers moving differently through space-time may disagree about the order of distant events. What appears simultaneous for one observer may not be simultaneous for another. In our universe, the speed limit set by light keeps these differences from creating contradictions. Signals cannot outrun light. Therefore, information always travels inside the light cones we explored earlier. But if signals could move faster than light, they would escape those cones. In certain situations, this could allow messages to travel backward in time relative to some observers. Imagine sending a message that arrives before it was sent. A reply might be received before the original message was written. Cause and effect could become tangled in paradox. Relativity avoids these strange situations by enforcing the cosmic speed limit. The speed of light keeps the structure of space-time orderly. It ensures that the chain of cause and effect remains intact. Every influence spreads outward at a finite pace, and every observer, regardless of their motion, sees events connected by signals travelling no faster than light. This limit also shapes the way the universe evolves. Stars cannot influence distant regions of space instantly. Galaxies cannot interact with one another without waiting for light to carry information across the void. Even gravity, once thought to act instantly across space, moves at the speed of light. When massive objects shift or collide, ripples in space-time known as gravitational waves travel outward at that same cosmic speed. These waves were detected for the first time in 2015, when sensitive instruments observed space-time trembling after the collision of two black holes. The signals travelled for more than 1 billion years before reaching Earth, yet they obeyed the same universal limit. They crossed the cosmos at the speed of light. This constant speed acts as a kind of ruler for space-time. It determines how distances and durations relate to one another. If an event lies outside your light cone, it cannot influence you yet. If it lies inside, then a signal travelling no faster than light can eventually reach you. Light therefore becomes the messenger that connects the universe together. And because light always moves along the boundary of those cones, it defines the frontier between the possible and the impossible. Objects with mass must remain inside that frontier. Their world lines stay within the light cone. They experience proper time along their journeys. But photons live exactly on the boundary itself. They travel along the surface of the cone, connecting events without accumulating time. Their journeys define the ultimate structure of influence across space-time. In a quiet way, the cosmic speed limit does more than constrain motion. It organizes the entire universe. It shapes the paths along which energy flows, information spreads, and events influence one another. Without it, the structure of space-time would lose its order. With it, the cosmos becomes a carefully connected web of events, linked by signals travelling at finite speed. And along the very edges of that web travel the photons that bring light from distant stars to our eyes. To us, their journeys stretch across unimaginable distances and vast stretches of time. But along the photon's own path, the geometry of space-time records no ticking clock. Billions of years may pass for us, yet along the light-like path connecting those events, time remains silent. This brings us back to the quiet mystery with which we began. How can something travel across the universe for billions of years, yet experience no passage of time at all? To answer that question fully, we must step back and reflect on the deeper meaning of time itself, and on the surprising possibility that the universe contains no single master clock governing everything. Let us return to the quiet puzzle that began our journey. Somewhere in a distant galaxy, a star shines. Deep within that star, nuclear reactions unfold in its core. Hydrogen atoms merge, releasing tremendous amounts of energy. Part of that energy escapes as light. At a certain moment, a photon is born. It slips free from the star's surface and begins a journey into the vast darkness between galaxies. From our perspective, this journey is incredibly long. The photon travels through empty space for millions of years. Perhaps it drifts past entire clusters of galaxies. Perhaps it crosses enormous cosmic voids where almost nothing exists. Time continues to pass. Stars are born and die. Galaxies collide and merge. Entire civilizations might rise and fall on distant worlds. All of that unfolds while the photon quietly continues its path through the universe. Eventually, after an immense stretch of time measured by our clocks, the photon reaches Earth. It might enter the lens of a telescope, it might strike a detector inside an observatory, or it might land gently on the retina of your eye as you look up at the night sky. When that happens, the journey is complete. From our perspective, billions of years may have passed between the moment the photon left its star and the moment it arrives here, but relativity tells a very different story about the same journey. To understand it, we return to the idea of proper time. Proper time measures how much time accumulates along the path taken by an object through space-time. For travellers moving slowly through space, proper time flows almost exactly as we expect. For travellers moving very fast, proper time slows. Their clocks tick more gently. Their aging unfolds more slowly. But when we examine the path taken by light itself, something extraordinary appears. The geometry of space-time assigns zero proper time to that path. This means that along the photon's journey, no time accumulates at all. From the perspective of space-time geometry, the emission of the photon and its eventual absorption are connected by a path where the clock never ticks. In our everyday experience, this idea can feel almost impossible to imagine. We're used to thinking of journeys as sequences of moments. First comes the beginning, then the middle, then the end. But light does not experience its journey in that way. Instead, the beginning and the end of the journey lie directly along a light-like path through space-time, separated by enormous distances in space, yet not separated by time. To see why, imagine again the space-time diagram we discussed earlier. The vertical direction represents time, the horizontal direction represents space. Objects moving slowly trace paths that rise mostly upward through time. Faster objects tilt more strongly sideways, and the paths taken by light lie exactly along the boundary defined by the light cone. Along those boundary paths, the space-time interval, the quantity that determines proper time, becomes zero. In simpler language, that means the universe assigns no elapsed time to the journey of light. The photon leaves its star, it arrives at its destination, and along the path connecting those two events, no proper time passes. It is as if the photon crosses the entire distance of the universe in a single, timeless step. This does not mean the photon perceives the universe in any meaningful sense. Photons do not carry clocks or consciousness. They cannot observe their own journeys. But the mathematics of spacetime reveals a deep structural truth about their motion. Light connects distant events in a way that bypasses the passage of time, and this idea helps explain why the speed of light plays such a central role in the laws of physics. Because light moves along paths with zero proper time, those paths mark the boundary between different kinds of motion in the universe. Objects with mass remain inside the light cone. They accumulate proper time. They experience the steady unfolding of moments. Light travels exactly along the surface of that cone. Its path belongs to a special category where time does not advance. In this way, photons act like messengers, linking distant events across space-time. When you look up at the night sky and see the faint glow of a distant star, the light entering, your eyes may have travelled for thousands or millions of years. Yet along the path taken by that light, the geometry of space-time connects the star and your eye, without any passage of proper time between them. The ancient light you see tonight began its journey long before human history. But in the silent language of space-time, the beginning and end of that journey remain neighbours along a single light-like path. The universe, in its quiet elegance, allows light to cross unimaginable distances while carrying no experience of time along the way. This remarkable fact reveals something profound about the nature of reality. Time is not an absolute river flowing equally everywhere. Instead, time depends on the paths taken through space-time. Different journeys accumulate different amounts of time, and along the paths taken by light, time disappears entirely. Understanding this strange truth leads us toward one final realization. If light experiences no passage of time, then perhaps the universe itself does not contain a single universal clock ticking for everything. For most of human history, time felt simple. There was yesterday, today, and tomorrow. There was the present moment, the quiet instant we call now. It seemed natural to imagine that the entire universe shared this same moment. If something happened on Earth right now, we assumed that there must also be a single right now occurring on distant planets, distant stars, and distant galaxies. In this familiar picture, time flows everywhere at the same pace, like a great river carrying all events forward together. But relativity quietly dissolves this idea. When scientists began to examine the behaviour of clocks moving at different speeds, they discovered something remarkable. Not only can time flow at different rates for different observers, but the very notion of a universal present moment begins to fade away. In relativity, there is no single cosmic clock governing the entire universe. Instead, each observer carries their own measure of time along their path through space-time, and different observers may disagree about which distant events are happening at the same time. This idea is called the relativity of simultaneity. To see how it works, imagine two observers watching events unfold in space. One observer stands on Earth. The other rides inside a spacecraft travelling at a very high speed. Suppose two distant stars explode at nearly the same moment, one far to the left of Earth and one far to the right. To the observer standing on Earth, the light from both explosions arrives at the same time. They conclude that the two stars exploded simultaneously. But the observer inside the fast-moving spacecraft may see things differently. Because they are moving relative to the stars, the distances between events and the timing of signals reaching them shift slightly. The spacecraft observer may receive the light from one explosion before the other. When they analyse the situation using the rules of relativity, they may conclude that the explosions did not occur at the same time after all. For them, one event happened earlier than the other. Neither observer is wrong. Each is simply using their own frame of reference to measure events across space-time. Relativity shows that simultaneity, The idea of events happening at the same time is not absolute. It depends on the motion of the observer. This discovery can feel deeply unsettling at first. Our everyday experience encourages us to believe that the present moment exists everywhere at once. But the universe does not appear to organize itself that way. Instead, space-time contains many possible slices of now, each corresponding to a different observer's motion. Two observers moving differently may divide space-time into past, present, and future in slightly different ways. Yet the laws of physics remain consistent for all of them. The light cones we explored earlier help maintain this consistency. They define the boundaries within which cause and effect can occur. Events inside your past light cone can influence you. Events inside your future light cone can be influenced by you. But events outside those cones remain beyond the reach of immediate cause and effect. Because signals cannot travel faster than light, no observer can receive information about events outside their light cone. This prevents disagreements about simultaneity from creating contradictions. Even though observers may disagree about the timing of distant events, they will always agree about cause and effect within their shared light cones. The universe preserves a consistent order of events where influence is possible. In this way, relativity replaces the idea of a universal clock with something more subtle. Instead of one master timeline governing everything, the universe contains a vast network of personal timelines. Every observer carries their own proper time. Every world line traces its own journey through space-time, and the relationships between those journeys are governed by the geometry of space-time itself. This picture may feel unfamiliar at first, but it reveals something beautiful. The universe does not impose a single rigid timeline on everything that exists. Instead, time becomes something more personal. Your experience of time is tied to your motion, your path, and your place within space-time. Different observers weave different threads through the same cosmic fabric, and yet those threads still fit together perfectly within the larger structure of the universe. When we consider light within this picture, its role becomes even more remarkable. Photons move exactly along the boundaries that define these relationships. Their paths form the edges of light cones. They connect events across vast distances without accumulating proper time. In a universe without a universal clock, light becomes the messenger that ties events together. It carries information across the cosmos while obeying the cosmic speed limit that preserves causality. And in doing so, it reveals that time itself is not a single, universal river flowing through space. It is something shaped by motion, by geometry, and by the paths taken through space-time. Understanding this opens the door to an even deeper way of thinking about time. Perhaps time is not a river at all. Perhaps it is more like a landscape, one where every traveller follows their own path across the terrain of the universe. For centuries, people have imagined time as something that flows. We speak of time passing, of moments drifting away, of the future approaching us like a distant shoreline. In poetry and everyday language, time is often compared to a river, steady, unstoppable, carrying everything forward. This image feels natural because our daily lives unfold in a simple sequence. Morning follows night, one heartbeat follows another, memories gather behind us while the future waits ahead. But relativity gently invites us to see time in a different way. Instead of a river flowing through the universe, time may be better understood as something woven into the structure of space-time itself. In this view, events do not drift past us like leaves on a stream. Instead, they occupy positions within a vast four-dimensional landscape. Your life becomes a path through that landscape. Your world line traces a thread through space-time, connecting the events that make up your story. Each step you take, each word you speak, each thought that passes through your mind becomes part of that path. and the time you experience, the steady rhythm of seconds and minutes, is simply the proper time accumulated along that path. For objects moving slowly through space, this proper time unfolds at a familiar pace. Our clocks tick steadily, our bodies age gradually. The river metaphor works well enough for everyday life. But as soon as motion through space becomes extreme, the illusion begins to dissolve. Relativity reveals that different travelers moving through space-time can experience different amounts of time. Two astronauts following different journeys through the universe may reunite having aged by different amounts. Their world lines through space-time contain different lengths of proper time. The river of time has quietly split into many personal streams, and each traveller follows their own current. Seen from this perspective, time begins to resemble a path rather than a flowing substance. The universe becomes a landscape of events connected by world lines. Every object traces its own route through that landscape, and the amount of time experienced depends on the geometry of the path taken. This idea may sound abstract, but it leads to an elegant picture of reality. Instead of imagining the universe as a stage where events unfold moment by moment, we can imagine space-time as a complete structure. All events, past, present, and future, exist within that structure. Different observers simply move through it along different paths. The passage of time then becomes something like travelling through a landscape. As you walk along a trail through mountains or forests, you experience the scenery unfolding step by step. Yet the entire landscape already exists around you. Relativity suggests that space-time may be similar. Events occupy positions within a four-dimensional structure, and your proper time measures how far you travel along your path through that structure. This way of thinking about time also sheds new light on the strange behaviour of photons. Light does not wander slowly through the landscape the way massive objects do. Instead, photons follow special paths that lie exactly along the boundary defined by the speed of light. Along these paths, the geometry of space-time assigns zero proper time. It is as if the photon leaps across the landscape without taking any steps along the time direction. The star that emits the photon and the telescope that receives it are connected directly along that light-like path. From our perspective, the journey may span millions or billions of years, but along the photon's own route through space-time, no time accumulates. The beginning and the end of the journey lie together along the same thread of space-time. This strange property reminds us that time is not an independent substance flowing everywhere at once. Instead, time depends on motion. It depends on the geometry of space-time. It depends on the path taken through the universe. Massive objects wander through space-time with a mixture of motion through space and motion through time. Light moves entirely through space, leaving none of that motion available for time, and that is why photons connect distant events across the cosmos without experiencing the passage of time themselves. Seen this way, the universe becomes a beautifully ordered tapestry. World lines weave through space-time like threads in fabric. Some threads rise mostly through time, others tilt strongly through space, and the delicate threads traced by light form the boundaries that connect events across the entire cosmic web. When we look up at the night sky and see the faint glow of distant stars, we are witnessing those threads of light arriving after journeys that began long before human history. Each photon carries with it a connection between two events separated by unimaginable distances. Yet along that connection, time itself remains silent. And this realization brings us gently toward the final reflection in our journey. If light can cross billions of years of cosmic history while experiencing no time at all, what does that reveal about the nature of time and about our place within the universe? Let us return one final time to the quiet traveller that began our story. A single photon of light. Somewhere in the distant universe, Long before human history, a star released that photon into space. Perhaps the star lived in a galaxy so far away that its light began travelling toward us when the Earth itself was still young. Perhaps the photon began its journey before the first forests appeared on land, before the first animals crawled from the oceans, before the first humans looked up at the sky and wondered what the stars might be. From our perspective, the photon's journey is unimaginably long. It travels across enormous cosmic distances. It drifts through regions of space where entire galaxies slowly spin and evolve. It passes through darkness so vast that even light takes millions of years to cross it. And while that journey unfolds, time continues to pass for the rest of the universe. Stars ignite and fade. Galaxies collide and reshape themselves. Planets form and disappear. Life begins, changes, and sometimes ends. All of this unfolds during the photon's long voyage across space-time. Eventually, after crossing unimaginable distances, the photon reaches our small corner of the universe. Perhaps it enters a telescope on a mountain. Perhaps it strikes a detector aboard a spacecraft orbiting Earth. Or perhaps it reaches your eye as you stand beneath a quiet night sky. In that moment, the journey ends. From our perspective, the photon may have travelled for millions or billions of years, but along the photon's own path through space-time, something extraordinary is true. No time has passed at all. The event where the photon was emitted and the event where it is absorbed are connected by a path along which proper time is zero. In the geometry of space-time, those two events sit along a light-like connection, separated by distance, yet not separated by time. To us, the photon seems to carry ancient history across the universe. The light reaching our eyes tonight may have left its source long before the rise of human civilization, but from the viewpoint encoded in the structure of space-time itself, the beginning and end of the photon's journey remain, neighbours along a single thread. This strange fact reminds us how deeply relativity has reshaped our understanding of time. Time is not a universal clock ticking the same way everywhere. It is not a river carrying the entire universe forward in a single flow. Instead, time depends on motion. It depends on the paths objects follow through space-time. Massive objects move partly through space and partly through time. Their internal clocks tick steadily as they travel through the universe. But light moves differently. Photons travel entirely through space at the cosmic speed limit, and because of that, their motion leaves no room for the passage of time. The geometry of space-time simply connects the start and end of their journey along a path where the clock never ticks. In this sense, light acts as a bridge between distant events. It links stars, galaxies, and observers across the vast fabric of space-time. Every photon arriving from the depths of the universe carries with it a connection between two moments, one when it was created and one when it was received. Yet along that connection, time itself remains silent. When you look up at the night sky, the stars you see are not only distant in space, they are distant in time. Some of their light has been travelling toward us for hundreds of years, some for thousands, some for millions, and some of the faintest light we detect in our telescopes began its journey billions of years ago, when the universe was far younger than it is today. The sky becomes a window into cosmic history, yet every one of those ancient photons travelled along a path where the passage of time never accumulated. Their journeys connect distant events across the universe with no proper time between them, and this realization invites us to see the cosmos in a new way. The universe becomes a vast network of events connected by threads of light. World lines weave through space-time like delicate strands of fabric. Some threads belong to planets and stars, slowly accumulating time as they move. Others belong to travellers exploring distant regions of space, and the luminous threads traced by photons stretch across the entire cosmic tapestry, linking events separated by unimaginable distances. Somewhere, even now, photons are leaving distant stars and beginning journeys that may last billions of years according to our clocks. One day, far in the future, those photons may reach the eyes of observers who have not yet been born, but along their silent path through space-time, the beginning and end of the journey will remain connected without the passage of time. And so, we return to the simple question that guided us through this exploration. Why does time stop for light? The answer lies in the deep geometry of space-time itself. Light travels at the cosmic speed limit. At that speed, motion through space leaves no motion remaining for time. And along those special paths, the universe quietly sets the passage of time to zero. From our perspective, light may wander for billions of years, but within the silent language of space-time, the journey of a photon begins and ends in a single timeless step. And perhaps, the next time you step outside on a clear night and see the faint glow of distant stars, you will remember that every point of light in the sky is a messenger from another time, a traveller that crossed the universe without experiencing time at all, a quiet reminder that the cosmos is stranger, deeper, and more beautiful than our everyday experience might suggest. And now, as our journey through space-time comes to a close, you might allow your thoughts to drift gently outward, like starlight travelling across the quiet darkness of the universe. Somewhere, far away, another photon has just begun its silent journey.